Yeah, hello once again and welcome to my YouTube channel. In this video, we're going to look at the methods of Lagrange multiplier, the processes to follow in order to solve Lagrange multiplier problem. So let's first of all look at what Lagrange multiplier is all about. So Lagrange multiplier, Lagrange method is used for maximizing or minimizing a general function of the form um, f, x, y, and z. Yeah. Um, subject to the constraint of the form g, x, y, and z equal to k constant. Lagrange multiplier is another way of finding extreme values given the objective functions and constraints. The method is named after a French mathematician, Joseph Louis Lagrange, who popularized it. It is a mathematical method of constraint optimization where constraint has a number of variables that ordinary differentiation of function cannot give an ideal solution. The Lagrangian multiplier is usually represented by lambda. Lambda is symbolized by this Greek alphabet. Is then introduced into the function, thereby converting such function into an implicit or composite function. The method is used in economics, management, construction, agricultural technology, etc. So let's look at the methods of Lagrangian multiplier. The method of Lagrange multiplier. So in order to find the extreme of function, f, x, y, which is a subject to the constraint, subject to the constraint g, x, and y equals to k. In this case, we're looking at a two-variable Lagrange multiplier. We follow the procedures below. These are the procedures we follow. The first procedure, number one, form a composite function, otherwise known as Lagrange function, which is as follows: L, x, y is equal to f, x, y, and then minus lambda, and then g, x, y, minus the constant. Yeah. So the composite function is made up of objective function. Our objective function is f, x, y, right? Combined with the constraint function multiplied by lambda. We already know that our lambda is what? This is our lambda, right? Yeah. So, when we multiply the lambda with the constraint, we have what? We have lambda, and then open bracket. The constraint is of the form x, y, and then don't forget the constant. Yeah. So this is the first step to follow, and then the second step, which is the second step, which is number 2, number 2, yeah, we take the partial derivative with respect to each variable x, y, and lambda. So we take derivative with respect to x, we take derivative with respect to y, and then we take derivative with respect to lambda of the composite function. So we already know that our composite function is L, x, y, right? Which is equal to f x and y minus lambda, and then our constraint is x, y minus the constant, isn't it? This is our composite function. So taking the derivative with respect to x will be Lx, which is equal to change in L over change in x. And then we also have Ly, which is equals to change in L with respect to change in y, right? And then we also have L lambda, which is equal to change in L with respect to change in lambda, right? So this is the second step in solving the Lagrange multiplier. The third step, that's number 3, is set each of the partial derivatives equal to 0 to get, we set each of the partial derivative equal to 0. And when we do that with the first derivative, which is Lx, the same thing as change in L, change in x equal to 0. And then we have Ly, which is equals to change in L, and then change in y, equate it to 0. And then we have L lambda, which is the same thing as change in L, change in lambda, which is equal to 0. And then we proceed to solve for x and solve for y in terms of lambda. Then substitute the solutions for x and y so that we are going to have L lambda is equal to 0 is in terms of lambda. Then solve for lambda and use the value to find the optimal values of x and y. So these are the steps to follow when solving a Lagrange multiplier. Yeah, so I think in order to make it much more clearer, we'll look at maybe an example to see how these steps can be applied. So the example that we're going to look at is, given example 1, given the following functions, given the following functions, and the functions are f, x, y equal to x, y, subject to g, x, y equal to x plus 2y equal to 2. Determine the value, this is V, please. Determine the value of x and y. So solution. So the first thing to do is to form the composite function. I already know the composite function is L. This L stands for Lagrange, you know. So L is equals to the objective function is fxy, right? And then we remember we multiply the constraint with lambda, and then we have our constraint to be what? X, y, yeah, minus k, right? Yeah. So this is our composite function. So going to the next slide, we have to note that that our f(x, y), that's the objective function, as given in the equation is what? Xy, right? And then our g x y, as given in the equation is what? X plus 2y, which is equal to 2, right? Or we can say our g x y is equal to x plus 2y minus 2. That's if you take everything, to one side. Therefore, we're going to get the Lagrangian composite function as xy minus lambda, yeah, sorry, let's undo, xy minus lambda, and that will be x plus 2y minus 2. I hope we're following. Yeah. So now we take the derivative with respect to x, which is our Lx. When we do that, what we're going to get is Lx is the same thing as change in L all over change in x. That's a change in Lagrangian as a result of change in x. And what we're going to get is y, right, minus, if you differentiate x here, is 1. So then this is constant, this is constant, and differentiating constant is equal to 1. So 1 multiplied by lambda, we are going to get lambda, right? And then remember, we equate it to 0. And then when we do that, we now have y minus lambda equal to 0. So we can now say we have y is equal to lambda, right? Yeah. Y is equal to lambda, or if we like, we can say lambda is equal to y, right? And then we can call this equation 1. So going to the next slide, we take the derivative with respect to what? Ly, and which is the same thing as what? Change in L as a result of change in y. And what we are going to get is x, right? And then minus, when we differentiate with respect to y, from the composite function, we know that if you differentiate 2y, you are going to get 2. So what we are going to get is 2 lambda, because when you multiply 2 by lambda, you get 2 lambda. And then don't forget to equate it to 0. Yeah, and then we can now convert this into proper, let's make lambda the subject formula. So what we have gotten is x minus 2 lambda equal to 0. And then we can say x is equal to 2 lambda. And then we can say, we can divide both sides by 2. So we have x all over 2 equal to lambda. So we can as well say lambda is equals to x whole over 2. We can call this equation 2, right? Yeah. So the next thing to do is, let's go to the next page. Yeah. So the next thing to do is to differentiate the composite function with respect to what? Lambda. And that will be the same thing as change in L all over change in lambda. And what we are going to get is exactly the constraint function, which is what? X plus 2y minus 2. Don't forget to equate it to 0. So what we have is what? X plus 2y minus 2 equal to 0. Yeah. And then in most cases, it's proper for us to take the constant to the other side. What we're going to get is x plus 2y is equal to 2. So we can as well call this equation 3. Yeah. So for us to find the value of x and y, we have to equate lambda is equal to lambda. Remember, we have a value of lambda in equation 1, and then we also have a value of lambda in equation 2. Yeah, for our lambda in equation 1 is the same thing as y, and then our lambda in equation 2 is the same thing as what? X whole over 2, right? So we have to solve for this, and then we can call this equation 4. Equation 4, yeah. So substitute y equals to 2x into equation 3. Substitute y equals to 2x into equation 3. And once we do that, we are going to get x plus 2. And then instead of y, we now have x all over 2, right? And then it's equal to 2. Yeah. Next page. So if we multiply, we have x plus 2x all over 2 is equal to 2. And then when we divide 2 by 2, we have x plus x equal to 2. And then x plus x is what? 2x equal to 2. And then our x is equal to what? 2 divided by 2. And our x will be equal to 1. That is the value that we're going to get for x. So that I have to divide this into 2. To optimize the space. Yeah, so since we've been able to get the value of x as 1, we can now get the value of y by substituting x, substituting x equal to 1 into equation 4. Remember, our equation 4 was what? Our equation 4 was y equal to x all over 2. Yeah, for our y is equal to 1 all over 2. So we can confidently say, therefore, our x is equal to 1 and our y is equal to 1 all over 2. So these are the methods of Lagrange multiplier. Actually, Lagrange multiplier is usually simple to solve, especially if you have just 2 variables and maybe just 1 constraint. Yeah, so if you follow the methods, you surely arrive at the answer. Yeah, so thank you very much for staying to the end of this video. Please share and subscribe to this channel as more and more questions will be looked at that will benefit you. Thank you and have a nice day. Bye.